welcome you all, and it's a good opportunity to interact with you all. I'm sure you all will find it quite interesting and effective, and will definitely help you to move further into the chromatography areas, specifically HPLC. So, starting with a bit of basics, not much in detail because Dr. Datar has definitely covered a quite good basic session yesterday. So, it has helped me to reduce my slides in terms of basics. What I would like to say is in simple language or in a simple sentence, if we say, or a simple line, LC is nothing but if you can dissolve, I can resolve. That's the definition of LC. GC is if you can evaporate, I can separate. And mass spectrometry, though it's a detector, it says if you can ionize, I can recognize. So this is in single line the definition of. So please remember, if you can dissolve, you can do the HPLC. If you cannot dissolve, you cannot do the HPLC. This is what yesterday Dr. Datar has discussed. But chromatography began with a Russian scientist, and and I think that is some good contribution coming to our life, that we all chromatographers are earning and running our homes because of chromatography. So I think we need a kind, or we have an obligation from him. Now, why we do chromatography? We do chromatography because we want to know composition, that is qualitative analysis. We do chromatography because we want to know content, that is quantitative. And definitely the commerce, because qualitative and quantitative research purpose, definitely people do it. But more aspect is that even research or analytical development or anywhere, commerce is very much included, or is a major part of it, and that's how it happens. So three pieces for why and how we do it. We try to have separations between the components, we try to have the sensitivity, and we try to have the speed. So 3S is the main motto behind any chromatography, whether it is HPLC, whether it is GC, or it is any other technique in chromatography. So I'll say this, and I'll say nothing is perfect in chromatography. Maybe it's a bold statement. I believe it in is an optimized chromatography, which gives you best of the three requirements, and we work out the method in a way so it gives the desired results. Three components there in liquid chromatography, that is mobile phase, stationary phase, and the sample itself. And based on the interactions, I think that Dr. Datar covered in the yesterday. So based on the interaction, the separation happens and the elution happens, and you find different peaks coming out of in the chromatograph. Why we have to do so much of development in LC or chromatography is because day by day the things have started going up and up and up. Earlier people were interested in the main peak or the main component. Now people are interested in is the impurities and what is other than the main peak. And that's why the technology has to improve, and technology has reached to a zettogram levels, or you can say 10 raised to minus 21 concentrations. So from manual titration to TLC, GC, HPLC, GCMS, LCMS, and FTMS. So that is how the technology has developed and evolved, I will say. Another improvement has happened in HPLC is the reduction in particle size. We can see that in 1950 we started chromatography with 100 microns, but then it reduced to smaller and smaller particle size, and now we are working on a sub 2 micron particle size. Here there are two aspects which I would like to mention and highlight, is because of that you will understand what miraculous technology or what a hi-fi scientific technology chromatography is, specifically HPLC. When we work on the HPLCs, the regular HPLCs are working from at 400 bar, and UHPLCs or UPLCs are working up to 1200 bar. Now, 1 bar is nothing but equivalent to 1 kg per centimeter square. And 1 kg per centimeter square, if we see, then 400 kg per centimeter square, you can imagine what tremendous pressure will be. Just for an example, I would like to mention is that when bullet hits a target, it's around 77 kg per centimeter square pressure, which kills a person. 77 to 100, that's what I could refer to. So if it is 400 bar, it is almost 4 times the pressure of a bullet killing a person. So you can understand what kind of pressure it is. And because of that, it's a technology which we should respect, and we should try to, when we see HPLC, we should have a respect for that. And same way, if we see column, the columns generally what we are using nowadays, of course, the surface area is right from 200 to say 400 or 600 even meter square per gram. Now, if we say 350 meter square to 400 meter square per gram, that is equivalent to 2 tennis courts. Hope everybody has seen the tennis courts. If not, personally on TVs. And if we put 1 gram of material at the end of the tennis court, you will never be in a position to see. And this much of material is available in 10 to 15 centimeter 4.6 ID column. So you can imagine what a great technology it is. So please, now I think, I'm sure when you see HPLC or you see column, you will have a kind of smile on your face, and you will see a respect for it. It's not a simple material you are just taking out of the drawer. What happened, how the HPLC got established? Slowly but steadily from 1980 to 2020. Of course, major improvements and development happened up to 2006 or 2008. Thereafter, the improvements has started happening into detectors, mainly the LCMS. The thing is particle size reduction, which we discussed, from 10 micron to 5 micron to 3 micron to sub 2 micron. And the different phases, including the what we can say water compatible phases, and the helix technology, which allows you to do polar separations even on HPLC. Along with that, improvement in hardware, as we said, there are pumps, injectors, column ovens, everything which can bear pressure up to 1200 bar. Again, I am not going into the definition of 1200 bar. And high sensitivity detectors. Improvement in data management systems, the networking systems and network softwares and everything, and with that compliance. So everything has happened, and that's how the things has developed to the level regulatory compliance. When I'm saying compliances from US FDA or any other regulatory FDAs. So that is how the evolution of HPLC has taken from 80 to nowadays, and has come out as a major technology or technique which can analyze organics, inorganic, small molecules, large molecules, water soluble, water insoluble, everything. And that's why that is the advantage of HPLC, that it allows you everything, most possible things. And when a compound can be dissolved, if compound can be dissolved, you can do all kind of HPLC analysis. And next part is that you can extend it to purification or preparative chromatography. So you can purify the samples at small levels for analytical and characterization levels, and you can purify it to the grams and kilo levels for production. This has been discussed with by Dr. Datar very clearly, but I'll say there are three components: stationary phase, mobile phase, and solute or the sample. And based on the interaction, the separation happens. Difference between the GC and HPLC, major difference is basically volatility and non-volatility, or polarity and non-polarity. It has been defined in the next slide more. So the thing is that thermal level components can be analyzed in HPLC. Solubility is must. Both inorganic and organic, both components can be analyzed. Small and large molecules can be analyzed. It is a non-destructive technology, and both stationary and mobile phase are influencing the chromatography compared to GC, where more of the impact is overall from the column side. Coming to bit of a theory part, this has been discussed, but what I would like to say is that if we say chromatography is the main thing, or it's a movie, then resolution is the hero. And if you achieve a good resolution, you have three components which support you. We call it as heroine, or we call it as director, or we call it as a writer or lyricist or whatsoever. But if we can manage selectivity, retention, and column efficiency, resolution is bound to come. And that's how the overall chromatography works, and that's how we can work on the chromatography, whether it is liquid chromatography or it is GC. These are the three main things which has been explained over here. This is retention, so how good the retention is happening for the column, particular column, which is basically defined by K dash. Then selectivity, how good the peaks are separated. And third is the efficiency or theoretical plates, how good the peak shape and peak illusion is. So there are the three parameters which are very important in terms of HPLC or GC or anything. But thing is, I'll still say that perfection is not a word or buzzword. Knowing and working into ARDs and QCs, optimum is the best word for the chromatography. These are the equations which has been referred yesterday, so I'm not going into. But yes, the or that is basically is affected by column or system part, and that's how for a single column and single mobile phase. Capacity factor is mainly a mobile phase contributor. When single column is there, yes, you can change the capacity factors as you change the column. Selectivity, yes, it is changed by mobile phase or stationary phase both. And definitely, because these three factors are affecting resolution, so definitely the resolution is affected by all the all the aspects. Now the requirement is 1.5 for the related, closely related components, and 2.0 for the higher components or the non-related components or the other components in the HPLC. How this and can affect the resolutions or overall efficiency of the chromatography is shown over here. You can see a 150 mm column with 5 micron. The theoretical plates is 12,500. With 3.5, it is almost going double, and with 1.8 or sub 2 micron column, it is going further almost 1.5 times. So basically, we can say that as we reduce the particle size, efficiency increases. You can see that 150 mm column of 5 micron and 100 mm column of 3.5 micron gives you efficiency better than the 150 of 5 micron. So one of the factor which can improve or give an efficiency is the particle size reduction, and people have started doing it. And along with that, the benefit is with the particle size reduction is analysis time reduction to almost minus 33%. So 66%, 33% reduction means out of 3 HPLCs, you can use 2 and 1 is free for another analysis. And it can go up to, and the solvent saving is 80 to 90%. So 33% reduction means your occupancy of the HPLC reduces by 33%, and occupancy of analysis reduces by 33%. So that's a good economic, and at the same time you are saving 90%, 80 to 90% of solvent, which is a good economic benefit. There are another theoretical aspects of it and how the calculation affects. So you can see that when we there are changes which are happening because of the particle size reduction, but otherwise, if we try to have the length or another factor with which we try to increase or decrease the theoretical plate, you can see it is not much affecting unless and until we change the particle size. But yes, K dash to certain extent gives almost equivalent of variation which is happening with the theoretical plates, and alpha or select that. Here we can see that when we do this, it helps us giving a quite good boost in terms of separation. So this is another thing which I wanted to say. So very small change in alpha gives you. Now we have made some change in the session morning versus afternoon is that we are focusing more on the hardware part, and columns part we will be dealing in the last, and uh, to the extent required, and there will be a detailed session on the hardware or the HPLC part. The HPLC system consists of mobile phase, pump, then injector or sample valve, then column and thermostat, detector with data system, and a printer. So this is how it goes. Nowadays, printer is not required, because you can convert it into PDF files and can directly email it to the people concerned, or if hard copy required, you can go for it. This is a small depiction of, or you can say an animation of HPLC system, which shows how this HPLC system works. There is a stationary phase filled in the column, and that is along with that, and you have a mobile phase, which is basically a mix of aqueous and organic. And now when we start this functioning, we have injected the sample. You can see the pink dot moving, going into the column, getting separated, and it is coming out as a now reaching detector and giving peaks as per the sample or component separated. So this is in short what we can say is what happens in HPLC. So pump delivers. I have next slides coming in where functionality part, but this is in simple animation. We can say how the things happens on an HPLC. Here I'm trying to show the different components that you have, and solve mobile phase or solvent tray over here. Then you have a degasser, vacuum degasser. You have pump, which pumps the liquid. You have auto sampler. You have thermostat column oven, and you have a detector, which is attached to a data system, which is not shown here because we are talking about is the hardware. So now solvent tray, you have a mobile phase. Pump gives you the flow rate composition of the solvents for the separation. Injector gives you the is the cooling of the samples by cooling it, and injection of the sample as desired or as per the method requirement. So storage of the sample, storing in the appropriate condition, and injecting it. Column oven, where we are connecting the column, and at the same time we are maintaining it at fixed temperature, so that variation in the chromatography can be avoided. And finally it comes is the detector, which gives you a different kind of detections based on the detector selected, and based on that we can work out the things. Okay, coming to degasser. What does degasser do? Degasser is nothing but a vacuum chamber with a what we can say is a micro permeable polymeric tube through which the solvent passes, and it goes to the pump, and then this vacuum chamber takes away all the air which is present in the liquid, and this is, you can see the vacuum pump and everything in the degasser, and then a degassed solvent comes into the pump. And this is very important because when there is a gas in the solvent, it will create noise. You can see the chromatogram below. This is no degassing, this is helium degassing, and this is online degassing. So you can see the impact of it, and that shows that how online degasser is very important. Okay, I have explained this. So basically, this is the overall different kind of pictures which shows you how it happens and how the degasser is working. This is again, and this is the place where you find the degasser, or you can have a standalone degasser also. Okay, and those degasser comes into the pump. Now coming to the pump, what happens? Pump is having a pumping head which pumps the liquid with two check valves. One is inlet check valve and one is outlet check valve. It's a non-return valve. So when pump or piston moves on the back side, this valve opens because of the pressure, and it gives the liquid in. And when it comes in, it pushes the solvent out. This is a basically a cross section of a pump, which is just for your understanding. So what happens is that liquid pushes in from here, goes into the pump head, and then it moves out to the system. And this is the basically cam which uneven, so it can pull and push the piston. There is another which is a dual piston parallel pump kind of things, where there are two pumps. One is a primary pump and another is a secondary pump, to decrease the pulsation on the system or coming into the system, so that noise can be reduced. And there are dampener also in the pump, so that even remaining pulsation is removed by the dampener. Dampener is nothing but a kind of what we can say, a kind of elastic membrane which takes up the pressure shocks and passes the liquid out of it. without any pressure shocks. Isocritic system. This is a system where we are using single solvent. It can be a single solvent, means aqueous or solvent, organic base, or a pre-mix. Only one solvent in a one bottle is can be used for the analysis, and not more than one solvent can be used. Isocritic systems are being used with many systems, but majorly now isocritic system is used with RI detector, and isocritic system is not that much preferred by the analytical people is only because of the ease of operation in gradient and ease of separation or efficiency of the mixing of the solvents, and because of that reducing run times with better efficiency of separation. So there can be two kind of gradients. One is high pressure gradient and another is low pressure gradient. And this is a typical example that, okay, fine, how you do it in the isocritic mode, and you can see the poor separations, and how you can do the same with the gradient system. So that helps a lot with the gradient system, where you are increasing the organic content from 30% to 95%. So you're moving from polar to non-polar. So this is something which happens with very good effective separation with the lowest possible runtime. What we were talking about was the high pressure gradient and the low pressure gradient. In high pressure gradient, you have multiple pumps. Each pump is taking a single solvent and mixing after the pump. Pump mixing is happening after the pump. So this is something which is duplication of two isocratic systems, and mixing is happening after the pump, and that's why after the pump it's a high pressure zone. That's why it is called as high pressure gradient. Same way here, if we see, and this is a photograph of the pump, which is high pressure pump. You can see two pump heads, which is mixing over here and then going into the system. And this is a low pressure where there is a only single pump. This is the pump, and there are four solvents, four tubes you can see coming in, and four solvents are coming through degasser into a low pressure gradient or multi-proportionating valve. This valve takes the proportionating as per the programming, that 10%, 20%, 30%, 40%. We can vary A, B, C, D, all the four solvents, and that proportion is passed on to the pump, and then pump puts it to the system. Here also, if required, mixer can be used, but generally the mixing happens between the pump and a low pressure gradient or multi-proportionating gradient valve. So this is something which is low pressure gradient system. So I'm sure high pressure gradient system, low pressure gradient system, isocritic and gradient analysis is clear to you all. So now I'm moving to is injector. In injector, we have different kind of injectors. We can have a manual injector, or we can have an auto injector. Manual injector is where something you are injecting with a syringe and loading it onto the column with a different size of loop. This is the loop, if you can see in the background. And this is an electronic injector, which is part of the auto sampler, which we discussed earlier also. And then it has a loop fixed with it, and a syringe also, so that whatever volume required, you can use it without changing the loop. Here you have to change loop as per the requirement of the volume. This is a depiction, same depiction of whether it is a manual injector or an auto injector. What happens when we load? The thing is that when we load the sample comes from the auto sampler, goes into the loop, fills the loop, and goes out in the waste. And when we change and inject it, what happens is that the pump, at that time the pump is in isolation while the loading is happening. Pump and column are in isolation, and then when we take from pump, when we take it in the injection mode, the loop gets connected to the main system, that is pump and the column, and the things are loaded onto the column. So this is what happens exactly when we are doing it. Now this is something which is a simple example. There are certain cases where you have a dual valves. So in one you are loading it onto the syringe loop, and then you are injecting it with the loop. So there are two kind of samplers, needle in the flow path auto sampler, and here there are advantages that there is no sample loss, low carryover, and but the cost is very high and more delay volume. While automatic injectors with a on flow path is where what happens is that loop is in the path and you are filling up the loop, and then the injection is done. So this is what happens into the online injectors. Hope the overall operation of injector is understood, how it injects the sample. And there are two parts. One is the needle in the flow path, and another is the regular kind of isolated injector. Coming to column oven, I think I missed the slide with the syringe on that. But at the end of the session, if I can find out that second kind of auto sampler where syringe is on a different path and the column is on a different path, I will show it to you. Column oven. Column oven can be either block heater, where you have an aluminum block which is heating the or cooling the column, or forced air which comes into the column oven and it heats or cools the column. Here the better temperature equilibration, but once insulation, I think block heater also works equally well, so not much of the issues. But any kind of column ovens can be used. Why we use this is something which is a picture of a column oven. Why we use column oven is we want to maintain the temperature on the column while analysis is going on. Because if you vary the temperature, like in the general shift, when a mid-size organization is there which is not working in the shift, you have AC on, and you have put a sequence. In the night there is no AC on, so temperature of the room is different, and then you find a variation in the analysis. This is something which is showing you the variation because of the temperature. As the temperature increases, you have an issue coming in terms of linear velocity. Detectors. Coming to detectors, what we require is easy operability. It should be very much aligned with the requirements of the analysis requirement. It should be quick in responding because it has a small volume. So basically the pick passes very fast, and during that, if the signal is not picked up, then your chromatography is gone. Though column will separate, the detector will not detect it appropriately. No dispersion should happen. So basically what is happening is that after column to the detector is a no pressure zone. Pressure is existing only up to the column head. Thereafter there is not much of the pressure. So as soon as the pick comes out or the component comes out of the column, it starts dispersing. And when it reaches to the column, if the volume is very high, the dispersion will happen. You will lose on the resolutions, you will lose on the peak heights, and everything will happen because of that. Low resolutions, low detection limits, and everything will happen if delay volumes are not taken care of. So this is one thing which is very important. That's why the volumes or dead volumes or the flow cell volumes should be minimal. We'll be discussing here UV-VIS, photodiode, fluorescence, refractive, and mass spectrometer. Rest of the detectors I will not be going into the details because they are not much into the use. So this is a simple UV-VIS optics and most popular detector definitely. And here we are doing is a single wavelength detection. It can have a wide wavelength range, multi-wavelength detection possible. There are detectors who can allow you to do 2 wavelengths or 3 wavelengths, and that's how you can go. There is D2 lamp and there is a visible lamp, or and wavelength calibration is done automatically. So these are the features of the UV detectors, all brands across. And this is the basically a kind of graphics where you can see the UV lamp, you can see the mix lamp also, and then you have a cutoff filter, holmium oxide filter, you can have a wavelength slit. Then it comes out to the grating. Grating gives you the fixed wavelength selected, and then it goes through the flow cell where the sample is coming in, and then it goes to the sample diode. And this is the reference diode which takes the reference signal without sample effect, and then difference between the two is detected as a peak. So this is variable wavelength detector or UV-VIS detector. The benefit over here is that this is a very simple in operation, very less data generated in terms of size of the chromatogram, data of the chromatogram, or size of the chromatogram, and that's how occupies very less space in the data system. But at the same time, this is a UV-VIS is a QC detector, while when we move to the PDA or diode detector, there it is more a development detector. What happens over here is that the light source directly enters into the sample without any wavelength selection, and then it goes into the grating, which gives it all the wavelengths onto the diode array. The diode arrays are multiple in numbers. It can be 300 to 600, and based on that, one or two wavelengths, that is in nanometers, say 2 nanometer, 3 nanometer, 4 nanometer, 5 nanometer, or say 250 nanometer, 251 nanometer, 254 nanometer, will be accepted on the different diodes, and all the data will be saved and stored. Benefit here is that you have each and every wavelength chromatogram available. You have the scan of each and every component of the chromatography, and you can check each and every component for its peak purity, whether there is any merging of the peaks or not there. It gives a third dimension. So along with the time and absorption, it gives you the wavelength as a third dimension, increasing the specificity. Okay, so this is something which is a path flow, and I have just tried to show it how it works. And this is beautiful picture which has been shown over here. So you can see each and every component. Can you see this 2D picture over here? There are 1, 2, 3, 4 peaks and 5 peaks, sorry, and there are small peaks over here. But when you see it in the 3D, you can see that there is some peak or component over here also. There is one component which is over here. There are one component here, and there is a small peak which is definitely a good peak over here. So you have a complete idea about the sample what you have injected. We are getting a third dimension over here, and that is of the wavelength. And that's how it tells you that yes, there is something over here which is not seen at a particular wavelength which has been selected. So we can see the spectra at another wavelength, and we can try to understand and optimize the spectrum wavelength for that particular sample. And that's why this is very useful tool in ARD, or analytical research and development, or analytical development. Along with that, we can work out is on the peak purity. How we check on the peak purity? What happens is that we have a peak, and here on the peak we can have a different points where we can take the spectra and analyze the spectra. And we know that if it's a single component, it will have a complete same spectra all over the peak. But if there is a mixing of the peaks happening, you will have a different spectra at different points, and that will indicate you that there is something in, and which is called as a peak purity in simple words. But the software works in a very complicated way and gives you the peak purity. Okay, so in basics, this is very important tool, and you can see that the peaks are over. This is a, what you can say, a kind of TLC kind of iso-absorbance plot, which we call it as, has been shown over here. So I'm sure the UV-VIS and PDA detectors, you have understood the utility and advantages as a regular routine detectors in any analytical lab. Refractive index detector is a detector which is a universal detector, and I'm sure you all people will see this is being used when there is no compound having any kind of absorbance. Chromophoric groups are not there, so alcohol, sugar, saccharides, fatty acids, polymers, this can be used with so refractive index can be used as a detector for this kind of compounds, and we can obtain a quite good results. Flow cell is temperature control because it is required, because when you change the temperature, automatically your refractive index will vary. And what happens sometimes, specifically in refractive index detectors, we are using high temperatures. So there's high temperature solvent coming into the flow cell, which is cool. There will be a lot of noise happening and lot of refractive index change happening, which will affect directly onto the detection and directly onto the overall, what we can say, signal levels. But the limitation over here is that we can use only isochromatic pump, and pumps has to be very efficient so that there is no pulsation, so that noise level onto the RI detector can be reduced. This is a simple kind of, what you can say, opticals of the refractive index. I'm not going much into the details of it, but you can see that overall the flow cell of reference and sample both are at the same place. So change in or otherwise also change in the baseline, or that is by changing the mobile phase, you will have an impact on the sample detection. This is how it works. So I'm not going much into the details of it. Another detector, which is ELSD, or that is electronic light scattering detector, is an universal detector. What happens over here is that the sample coming in is nebulized in the nebulizer and then dried to convert it into a particle. And those particles enters into the detector cell where the light diffraction is measured rather than the direct light passing through, because the particles will diffract the light and that diffracted light is measured, and that's how it is. Now here the advantage is that this is an universal detector having a good sensitivity and gradient can be used. So this is the advantage of the ELSD. Then comes is a fluorescence detector, which is definitely a good detector, and there are few samples which is requiring detection with fluorescence by derivatization. That is what we do in derivatization. We derivatize the sample and make it fluorescent. This can be pre-column, that is basically sample derivatized and injected into the column, or post-column, means that after analysis the derivatization done for the sample, and that sample is detected by the fluorescence detector. What happens over here is that when we are giving the energy or exciting the sample or the molecule, when it goes back to the normal level, or then it releases the fluorescence, which is detected at the fluorescence detector. This is something what happens over here, almost the similar kind of as UV-VIS, but here the direct detection is not done. Detection is done of the fluorescence detection, and that is how. So the flow path of the light which is coming straight is not detected. Detection is done for fluorescent light at an angle. So this is how the fluorescence detector works. Mass spectrometer is a very good detector, and like diode array detector or photodiode detector, this also gives a third dimension. There we got is a wavelength. Here what we got is a mass of a particular component or a compound. The detection is definitely M by Z. Multiple charge proteins, which are large molecule, also can be detected with this detector. That is an advantage over here. And basically we have to ionize, as I said in the earlier slide, that if you can ionize, I can recognize. So this is the simple theory of mass spectrometer. Mind you, is a detector and not a system. HPLC is attached with mass spectrometer or mass detector and used as a detector, and that gives you overall sensitivity and detection. This is a typical mass spectrometer in a kind of. So basically the nebulization is done as it was in the electric detector earlier, ELSD detector, and here it is nebulized and then ionized. The and it is charged. So charged ions only migrate through this charged tunnel, and it reaches to the quadrupole. Of course, Dr. Rama will be explaining this far better in the next sessions happening tomorrow and day after. And then this is detected on the detector, and that is converted into. Along with this HPLC, the benefit is, this is the one thing which I was talking about, is that we can have a fraction collector which can help us in collecting the fractions after detection. Of course, in the mass spectrometer, there is a diversion has to happen because complete volume cannot pass through. But we can collect the fractions in a low level or high level, from like microgram levels to the milligram or gram levels, and that can be used for the characterization. That can be used for the R&D purpose, and when it has to reach to the level where we have to synthesize certain things, it can go to the production level also. So this is one thing which is fraction collector, which I have not shown in the earlier photographs of hardware, but this is one thing which is very useful tool, and this gives a big advantage. And all upscaling from analytical to the preparative levels can be done with a similar kind of column selections. This is a kind of fraction collector. So now this is a comparison of detector. In this we have UV-VIS and PDA detector have a sensitivity of +2, but fluorescence has better sensitivity. Refractive index has a very low sensitivity, and same way evaporating light scattering detector, electronic light scattering detector also what we call it as. So this is where it has a less sensitivity. Electrical conductivity has a better sensitivity or equivalent to the visible detectors. Electrochemical has a better sensitivity, but the mass spectrometer rules the scenario. So very good and useful tool in ARD. But nowadays, because of the specificity requirements, a very small mass spectrometers has been innovated, and people are started using it in quality control environment also. So this is brief on overall hardware system. I am sure I could justify it. This is the change we made from the morning session, is that we have focused on the hardware. And now coming to separation modes. So with HPLC, what kind of modes we use for the separation? And this is a graphic which can explain it very well. So we have on the y-axis is the molecular weight, and on the x-axis we have is the polarity. So on the what I will say is the left side is the non-polar and right side is the polar. And then in that also we can do the solubility part, that water insoluble part on the left side and water soluble part on the right side, and non-ionic polar, which is a in between group kind of thing. So non-polar, non-ionic polar, and ionic polar. So this is how it happens. Higher molecular weight, what we are doing is a size exclusion chromatography, gel and gel permeation is basically nothing but having with the organic water, and gel filtration is nothing but size exclusion with water miscible solvents, water and buffers. So this is size exclusion, basically a kind of flow technique through which because of the absorption and passing through the column, it happens as a separation based on the molecular weights. Coming to the lower size of the particles up to 1000, basically adsorption. Then in partition we have a reverse phase and normal phase, and then we have is an ion exchange. So these are the technique which is used for the small molecular weight samples, or what we call it as peptides or small molecular pharmaceutical molecules or chemical molecules and all those things. While here it is for the large molecules, which can be polymers, which can be biopolymers, or it can be chemical polymers, and that can be analyzed over here. So this is in small what we are doing. What is important when deciding a mode for HPLC is the solubility, as I have discussed, the picture I have shown, molecular weight, and then structure, whether it has a UV-absorbance or doesn't have absorbance, can it be derivatized, can it not be derivatized, can it be ionized, can it not be ionized. So these are the aspects which decides on the mode of chromatography. Now, reverse phase chromatography is the most preferred way of HPLC analysis, and people are doing a lot of reverse phase HPLC in analytical laboratories. Then comes is the large molecular weight, more than 2000, size exclusion, chiral column for optical isomer separations or isomer separations, chiral separations, stereoisomers or positional isomers with normal phase or adsorption, inorganic ions with ion chromatography. There is a very good session, I think it's on Friday, where ion chromatography is being covered. So I will not be covering it much over here in detail. And sugars, amino acids, short chain fatty acids with special columns. So this is a part of column we will discuss briefly if time permits. Otherwise, we will stop at the modes of chromatography. Now in the chromatography modes, normal phase, we have a polar stationary phase. Typical stationary phase are polar hydrophilic stationary phases like silica and alumina. Typical non-polar mobile phases like hexane, isopropanol, or methylene chloride, which are water immiscible, generally water immiscible solvents. And samples which are being used, for which it is used, is fatty acids and fatty and oily compounds, which are very highly non-polar and basically water immiscible or insoluble. Reverse phase, basically the column or stationary phase is non-polar. It is basically C18, C8, C4, C6, and those kind of compounds based mainly on silica, or it can be on polymer columns also. Solvents being used, water, methanol, acetonitrile, buffers, and ion pairing agents. Typical solutes, almost everything can be analyzed over here, and all organic components which are soluble. Ion exchange, it's basically ion bonding kind of stationary phases. Ionic functional groups on silica or polymer, that is the stationary phase. Mobile phase is water, buffer, acids, base. This is what the, so mainly this is aqueous. And typical solutes are any ion charge compound, means it has to has ion charge, or it should be in the charge form. It should be in ionic form. Chiral is basically the chiral recognition columns, the stationary phases, and chiral groups are attached to or bonded to the silica phases. This can be aqueous or it can be non-aqueous. So enantiomers, small and large molecules can be separated by chiral chromatography. Affinity chromatography, basically this includes the biomolecules attached or packed into a column, and that is being used for affinity column, where we are, it's an basically, if we say, then overall monoclonal antibodies, MABs, or there are other things where we are doing sample preparations, like we have to remove certain protein samples from the main samples so that minute components in the blood or plasma can be analyzed specifically in proteomics and metabolomics. Waters and buffers are used in this because solvents cannot be used because biomolecules are not stable with that. And typical solutes are biomolecules or their substrates. Size exclusion I have discussed. It's basically the column which has an appropriate pore size because of which the compounds are separated. It's gel type polymers and even silicas are being used. Two modes, aqueous and non-aqueous, both the modes are there. That is what we call it as gel permeation and gel filtration. And polymers, synthetic or biological or chemical. I think everything can be separated over here. So this is in simple. Now, instead of going much into the mechanism of ion exchange and those things, I'll prefer to go is directly onto the normal phase and reverse phase, if allowed. Hope that should be okay. So here what we are doing is basically we are doing is partition chromatography with a hydrophilic or what we can say stationary phase and non-polar, comparatively non-polar solvents. What we are using columns are silica columns, which is USP-L3, cyano columns USP-L10, amino columns L8, or diol columns L20. And these are the columns being considered as suitable columns for normal phase chromatography. And cyano and amino are typical columns which can be used even in reverse phase column. So if anybody is using cyano columns for both the usages, please get it shipped into the solvent which your use is. If normal phase, then get it shipped into the normal phase solvents. If it is reverse phase, then get it shipped into the reverse phase solvents. Diol and silica are generally used for the normal phase chromatography. Basic solvents are aliphatic hydrocarbons, aromatic hydrocarbons, basically water immiscible solvent. So that is what we are doing in that. This is a typical interaction which happens while separation. So here you can see that strong will be retained on the column and elute later, and weak fractions will have earlier elutions. This is the impact of the solvent polarity. Hexane is non-polar, methanol is polar. There's a separation over here, but as you increase the polar, you can see you can reduce the run times and you can have better or faster elution, and you can optimize the difference between the normal phase and the stationary reverse phase. The stationary phase is polar comparatively or hydrophilic in normal phase. It is low polarity or hydrophobic in reverse phase. Mobile phase is low polarity or hydrophobic in normal phase, and high polar or hydrophilic in reverse phase. Normal phase came in first because the HPLC or liquid chromatography arrived from the TLC or other paper chromatography and all those. So the normal was polar stationary phase and non-polar solvents. So when reverse phase was developed, it was called as reverse phase. So that's how it is reverse phase. Difference. Normal phase can allow is effective separation of structural isomers, which is a bit difficult on reverse phase, but nowadays people are doing it. Offers separation selective not available with reverse phase. So selectivity is different between the two. So it's offering a different selectivity. Stabilizes slowly and eluents are expensive. In reverse phase, wide range of applications, effective for separation of homologues, Stationary phase has long service life, so life of column is quite better here, stabilizes quickly, and eluents are less expensive. Stationary phase, low polarity in reverse phase, and mobile phase is high polar. Basically, water-based mobile phases are used, and the polar solvents like acetonitrile, methanol, like water miscible solvents are being used, and additives are also used. And then mixing ratio and pH makes the separation. These are the typical columns used in reverse phase: C18, which is USPL1, that is octadecylsilane; C8, octyl silane, that is USPL7; butyl L26, phenyl L11, trimethylsilane L13, and cyano L10, and as I said, amino L8. They are the columns which are being used in reverse phase chromatography, HPLC. And these are typical ODS chain length. You can see 18 chain molecules in the attached to silica molecule. These are the interactions. C18 gives a very strong interaction with nonpolar, C8 gives a medium, and C4 gives a weak nonpolar interaction with the nonpolar. This is how it happens. The elution pattern is the same: more interaction, less later elution, less interaction, faster elution. This is again the impact of the polarity. Methanol is comparatively non-polar, and water is comparatively polar. So as we increase the water composition, water is more polar. So as we increase the non-polar composition, it gives you a better reduction in the runtimes. Along with that, I would like to discuss is reverse phase ion pairing agent. As we have omitted this, if you allow, I will go back to ion chromatography a bit. What happens over here is that we are working with the ionic compounds in column, and ion exchange happens. But this is more for a polar components and polar separations which are into the ionic form. But here what we are trying to do is that polar compounds which are in ionic form are somehow bonded with the ion pairing agents, and it gives the non-polar impact onto the molecule, and along with that it neutralizes the charge, so it allows us to work on reverse phase environment, and that's how it happens and it works. So it has a dual impact. It can be ion exchange like effect also, and it can be ion pair formation also. It can be a dual kind of impact when the analysis happens. But equilibration is very, very important in this particular case. Of course, it is important in other cases also. It is highly important over here. And equilibration with ion pairing agent with the stationary phase is very important for the separation. What we are doing over here is that polar compound which is in ionic form, compound has to be in ion, so it should be at its what you can say pK value in the 100% ionic form, and we are attaching or bonding it with a chain length of C5 to C8, so it becomes non-polar, and then non-polar interaction happens and it becomes neutral, so no tailing impact coming in, and at the same time we have a separation happening with the non-polar stationary phase. Same way for anionic compound, we are using tetrabutyl ammonium hydroxide, which gives a similar impact for the anionic compound. Selection of ion pair agent is very important. pH of eluent is very important. Concentration of ion pair agent is also important because it has to bond at the same time, has to equilibrate with the column. So it has to bond with the eluent or the sample. Proportion of organic solvent in eluent is also important because that will impact the overall what we can say bonding and elution. So while coming to HPLC columns, main important thing over here are the physics part and the chemistry part of it. In physics, what we are talking about is the length and the diameter of the column, and of course the what we can say is the physical interactions. But chemistry is also important over here, and that is basically is related to the type of the surface, that is the phase what we are selecting, C18, C8, and all those things. Pore size, because that will allow the size of the molecule passing through the pore. Particle size, that is we have seen the efficiency, how the efficiency happens over here there, and along with the carbon load, because silica is a totally inorganic compound, so carbon load or the organic compound coming in from C18, C8, so it's basically bonding of the phase. happening into the column or into the stationary phase, that also has its own and surface area. For sure, surface area will go into the physical properties. So these are certain things which is very important in terms of column selection. So carbon load, pore size, pore volume, particle size, and the phase. These are the important things while choosing a phase for analysis of a compound. More important from the analytical development side, less important from the quality control chromatography. Because quality control doesn't have much of the variations possible. They go by what ARD says. This is a typical hardware. I'm not going much into the detail, but there are two kind of columns. One is the conventional column, and second is the cartridge columns. Cartridge column comes with hand fitting, and cartridges can be removed. Here it is a complete set of column which is to be used as a complete set. This is how the silica looks like, and these are the improved version of the silica. And you can see this is a vertical section, then this is a cross section. This is the porous. Silica is highly porous. That is very important. That with so much of high porosity, with high surface area, because of the porosity, it bears the pressure of 400 bar to 1200 bar. Nothing like silica is available in terms of stationary phases or stationary base phase for HPLC. So you can see the techniques which has developed has given a very good surfaces. This is how the typical C18 looks like. I'm not going much into the detail, but this is the surface of silica, and then these are the C18 chains which are attached to the silica surface. Sizes are very small, 21 angstrom or kind of things. I'm not going into much of the details of it. These are the different kind of columns like C18 phases, C18 or C8 or C1 or phenyl or PFP, just as a reference to you. This is very important. End capping of the columns or the end capping of the phases is very important, because once we bond the different phases, there is a possibility that complete closing of the selenol groups or the bonding of the selenol group doesn't happen. So in the second reaction, those leftover selenol groups are bonded with trimethyl selen or some polar compounds, and that's how it happens to be or becomes an end cap. So it doesn't react with the ionic forms, because when we operate into the low pH range, the selenol groups are in ionic form, and then basic compounds are also in ionic form, and they can interact and give you a pigtailing, and sometimes loss of resolution, loss of peak shapes, everything. There are hybrid particles. I'm not going much into the details, but it was advantageous when silica with higher pH range were not available. Now silica columns are available with higher pH range up to 12, 1 to 12. So people can use more that, because there are some disadvantages with hybrid particles. Organic particles, again, it was having the advantage of pH, but nowadays up to 12 pH, nobody generally goes beyond pH 12. So I think this is a quite good that we use silica, because main thing is low mechanical strength, low reproducibility, and low efficiency. Second, one more evolution which is happening in the phases is the water compatible. This is where I will say that when we take absolute pure C18 phases and we use more water, maybe 85% or more, the C18 phases collapses. What I will say is that if this is the phase, it falls because the water is polar and the phases are non-polar. So what happens, that chain is falls from the bonding phase and it loses its activity with the components, and that's how we call it as phase collapse. So nowadays, end capping, polar end capping, or embedding a polar component into the non-polar chain gives a better water compatibility and at the same time better polar separations. So this is something HPLC. HPLC is an area which is called as reverse phase also. Here what we are trying to do is we are using a reverse phase column and normal phase normal phase columns and reverse phase solvents, and there we are establishing a non-polar environment, polar environment, and doing a polar separation. These are different various phases for the selection. I'm not going into the details much, and these are the columns available for sugar and amino acid analysis. This is one thing which I would like to mention as a superior technology which is coming out, and that is a superficial porous particles, or what people call it as core shell technology. Here what happens is, as we saw, the regular silica particles are totally porous. If we cross section, you have seen it earlier. Here there is a solid core, and on that there is a porous layer of silica, which is so this can be polymer or something else. But this is something which is a silica with the porosity, similar kind of things as it happens in the polar particle. What happens is here there is a less of the path to be traveled by a molecule. While here it has to travel through the entire long. So with a small runtime, we can have the similar efficiency, and at the same time, you can see that peaks are what we can say sharper compared to the regular HPLC, and that's how with normal HPLC, that is 400 bar HPLC systems, we can achieve the UPLC or UHPLC performance. Any kind and every kind of samples can be analyzed with HPLC, right from toothpaste in the morning to the pillow having certain residual solvents or some kind of carcinogenic compounds. Everything can be analyzed on this. So I think I'll end over here, and I will thank you all for your time and attention. And I wish you all a success and prosperity, and enjoy your chromatography. Chromatography is based for any analytical chemist. Thank you so much.